Thank you for the introduction. Good afternoon, I'm Chija. So today I'm very happy to present our recent work, Polar tag, a new type of invisible tag encoding data with light polarization. So visual tags like QR code usually use their geometric patterns to encode data, such as URL or text. And this enables a lot of applications, such as object identification, public parking, or even mobile payment. However, given their harsh geometric patterns, they are always obtrusive, so they are undesirable to be embedded into ubiquitous objects. And another problem is they are not always robust. So they will fade in harsh ambient light conditions, and sometimes the detection range are not good enough for some applications. So in this work, we propose Polar tag, a new design paradigm of passive visual tag that is unobtrusive and robust. So I'm going to present how we use the light polarization and color to encode data. So let me first give you some background and our design rationale. So light is an electromagnetic wave which consists of oscillating electric field and magnetic fields. And the polarization is the oscillating direction of the electric fields as the light propagates. So direct sunlight and artificial light are usually unpolarized, so they are randomly oscillating electric fields, which means they contain all polarization direction. After passing through a linear polarizer, they only contain one polarization direction, but still all wavelengths, so we have polarized white light. So after we get in polarized white light, how can we generate colors from everyday tape? So we add the birefringent tape in. So similar to a prism that would split the light into different spatial directions according to the wavelengths, the birefringent material, like the everyday transparent tape, will disperse the light into different polarization directions. So after this, we would have dispersed white light, which means in each polarization direction, there contains only one single color. And if we add another linear polarizer after this, we could perceive the single color. And of course, if we change the direction of the second linear polarizer, the color will change. And the interesting phenomenon here is, if we change the thickness of the transparent tape, the color will also change. And if we change the orientation of the transparent tape, the color changes as well. So here is a quick demo of color changing. Sorry. Let me go back. This is a quick demo. If we change the direction, the color will change. If we change the thickness and orientation, the color will change as well. So with this background, our high-level design idea is we attach our tag to the object, and the light will pass through and reflect it back. And again, we have the dispersed light. So now if we add another linear polarizer to the camera, we could perceive the light. So with this background and rationale, let's take a detailed look at our Polar tag design. So we split it into three parts: encoding, detection, and decoding. So first, encoding. Obviously, we can manipulate the tape thickness and orientation to create color patterns to encode data. And the intuitive way is we divided the tag into different cells. And for each cell, we assign a tape configuration. And here, tape configuration means the combination of the thickness and orientation. So since each configuration will correspond to one color, we would have the multicolor tag. So if we have m tape configurations, each cell can then encode log m bits. In total, if we have n data cell, we can encode n log m bits. Then we can extract the data according to their color. However, if you remember, as I said, when the orientation changes, the color will change as well. So if we want to decode data in this way, we have to build a lookup table to store the colors of all configurations in all 3D orientations. And we need to know the orientation of the tag before decoding. So this requires heavy computation training and expensive computation. So to solve this challenge, we propose placing a reference cells at known positions on the tag, and we call them pilot cells. For each tape configuration, we would have one pilot cell. And then the remaining cells are the data cells that actually encode data using the same patterns with the pilot cell. So with this design, while the color will still change with the orientation, but by comparing each data cell's color to the pilot cell, we can recover it accordingly. So although this design slightly lowers the encoding capacity to n minus m log m, it greatly reduces the decoding overhead and removes the need for knowing the orientation. So with this design, two main questions arise. First, how to choose pilot cells? So one essential property of the pilot cell is they must be separable in all orientations. And at the same time, the color difference should be large enough to guarantee robustness. So in our experiment, we tested all tape configurations and selected 4 out of it, which strike the best balance for this particular size. Notice that here 4 is not a fixed number. You can change it according to your application. So as shown on the right, the x-axis is the angle, which is orientation, and the y-axis is the hue value, which you can interpret as the color. So you can see those 4 tape configurations are indeed separable in all orientations. And the second question would be how to place those pilot cells. So since occlusions usually happen in a cluster, if we put the pilot cells in a cluster, when occlusions happens here, we cannot decode any data. So we want to put them as far from each other as possible, but excluding the edges, because spreading the pilot cell across the edges, on the other hand, will lead to a greater color deviation between them. So in this way, even some parts are blocked, we can still decode the rest part. To further improve the encoding robustness, we add redundancies to our encoding by applying Reed-Solomon coding. So with RS coding, we group cells into blocks. Each block is the RS symbol. By processing each block, we can correct a certain number of errors and recover the original data. So after encoding part, let's move to the detection. So for detection, we leverage the color-changing nature of the polarization pattern. So we take 2 images in 2 different polarization directions, and this can be done on the fly with an LCD shutter. So from the 2 pictures, we can see that the background are almost constant. This is because ambient light are usually unpolarized. So if we take, and the only color changing area is the tag. So if we take difference of these 2 images, we can cancel out the background and only left our tag area. And this approach makes our detection more robust than the existing visual tags, which solely rely on the geometric pattern to do the detection. So our detection would have following steps. First, take 2 images in 2 different polarization directions, and then take the difference to get the rough region of interest. Then we would apply the contour finding algorithm to get the refined polygon, and then do the corner detection to get the 6 key points. So notice that here we cut the top left corner in order to get the orientation of our tag. So after getting the 6 key points, we can do a homographic transform to get the kinetic view of our tag. Then we can move to the decoding stage. Since we already have the kinetic view and we know where the pilot cells are, we can easily extract the hue and saturations from the pilot cell. And of course, we can also extract the hues and saturations from the data cell. And then we would compute the Euclidean distance between the data cell and pilot cell and match data cells to the closest pilot cell. And after the error correction, we can retrieve our bit streams. We also build a prototype to evaluate our design. So as you saw on yesterday's demo, our prototype consists of a Raspberry Pi connected to a USB camera and with an LCD shutter on it. And we fabricate a 13 by 13 centimeter polar tag with transparent tape and linear polarizer. And to evaluate our performance, we compare it with the same size QR code. So first, we tested the detection distance and decoding distance. So on the left, our setting is we put the tag on a movable platform and change the distance between the tag and the camera. And we show the result on the right. So the x-axis is the distance between the tag and the camera. And the y-axis on the top is whether the tag is detectable. And on the bottom is the bit error rate. So from the result, we can see that our polar tag can achieve 3 times longer detection distance than the QR code. and 2 times longer 0-bit error rate detection distance. And then we tested the viewing angle of our tag. So on the left, we put our tag on a rotational platform and rotated it from negative 90 degree to 90 degree with an interval of 5 degrees. And we show the result on the right. So the y-axis are still the same, and the x-axis is the tag angle. So from the result, we can get that our polar tag can achieve 1.8 times larger angular detection range and 1.4 times larger decoding angular range. And lastly, we tested the influence of ambient light. So in the experiment, we turn off all the other ambient light sources and use only one LCD as our light source. So we show the result on the right. The y-axis are still the same, and the x-axis is the light intensity. So in this graph, we can see our polar tag is still detectable even under very low ambient light condition, which is 7 lux. Then let me talk about some potential applications. First, augmented reality. So like I think in yesterday's talk, one presenter also mentioned that in some AR applications, users need to retrieve extra information out of the object. And this is usually achieved by adding some visual text. But this will sometimes interfere with the vision-based object identification. With polar tag, we can encode the extra information, but without changing the appearance of the object. So we can solve this problem. And the second application is robotic construction. So in robotic construction, usually the robot needs a visual tag to localize itself and get the orientation of the building blocks. Since our polar tag has a larger detection distance and larger angular range and better performance in low light condition, we can use this to facilitate this application. And finally, security side. So QR code as a payment method can be decoded at multiple orientations. So attackers can steal your money by taking a picture from the sideway. So we can leverage the orientation sensitivity of the polar tag to avoid this risk. So if we remove the pilot cell and use the intuitive design that I mentioned, then we can encode the correct information by a specific color pattern that can only be retrieved at a certain angle. So in this way, attackers cannot get the information from the site. And lastly, future work. So the first interesting direction we would like to explore is to use the polar tag to facilitate the post-estimation. So as we mentioned before, the color will change according to the orientation. So the most intuitive way is we can build a mapping from the color to the orientation. Once we detect a certain color, we know a certain orientation of it. And a longer-term interesting direction is building polar tag with non-linear shapes. So unlike other visual tags, polar tag is not restricted to be a square for tag detection. And also, since it's invisible, a polar tag could cover an object's entire surface. So this could first increase the encoding capacity. And second, since the area is larger, it can improve the decoding robustness. So like here, we put the tag on a mug, and we can still detect it because we can use the color-changing nature of the polarization. But then the challenge here would be, how can we transform the shape and identify the pilot cell? So this is still an open challenge. And this concludes my talk. Thank you very much. I'm very happy to take any questions.